Facebook for the last 4 or 5 years, and then I started a company called Qubole. I'm most famous as the guy who started the Hive project in Facebook, but I spent a lot of time doing stuff on Hadoop, so that's what I'm going to talk about. So the topic is cloud-friendly Hadoop and Hive. It's very fitting. It's a lot of clouds outside. Right. Oh, where's my vital instrument? Right. So I want to give you a quick introduction about what Qubole is, what we've tried to build. So that kind of gives a setting into the next two things, which is how we have modified Hadoop and Hive to work especially well in the cloud. So I'll try to, in each one of these slides, do a mix of like product vision, like what we wanted to create, and then try and go a little bit deep into specific technologies that we added inside this stack to make the product vision come true. All right, so what is Qubole? So when we started this company about a year and a few months back, what we found was that a lot of people were struggling to put big data stacks together. There's Hadoop, of course, but then there are so many of the other components, like which log collection service should I use, which workflow management system should I use, how do I put them all together into one thing that provides a service within my organization. So what we decided was to try an approach where we would set up everything in the cloud, where people would not have to understand the complexities of which technologies to use, how to integrate them together, and so on and so forth. We would just take care of all of that stuff. So this is sort of a core stack where we run in Amazon, and we're also looking at other clouds. But we provide all of the well-known big data components, obviously Hadoop, but then also things like Oozie, Hive, Pig, Sqoop. It's all hidden under our umbrella. And our umbrella is an API that just makes all of these things accessible very easily to people who don't have to actually understand how these technologies work or how they have to be integrated. As a user of our service, what you will find is that we interact with all of your data assets. So your relational data stores like MySQL or Oracle, where you're storing your user data or campaign data, your log files in S3, and your data marts like Vertica or Redshift. So we can pull in data from these different sources, feed it all into the big data stack that you don't have to touch and manage and stuff. And then you can focus on what you want to do, like which is analysis, integration, and so on and so forth. And in many cases, then push data back out into data marts like Vertica or Redshift. So there are two ways of accessing our sort of service. There is, of course, the API access, which is used by very technical engineering folks. For the vast majority of the users, they love the browser-based interface. So they just log in, and they are able to visually do, explore the data sets they have, integrate it all in one place, analyze it, and we are also working on some forms of visualization. Finally, there are also connectors available to traditional tools like Tableau, Pentaho, Excel. So we do have a ODBC connector, and so you can also connect to your favorite desktop productivity tool through these ODBC driver. So for the purpose of this talk, this is a lot of stuff to do within a small company and to cover in a presentation like this. So what I thought I would do is just focus a little bit on Hadoop and Hive, which is where we have spent quite a bit of our time. It's obviously, Hadoop, as you saw, was the central sort of the linchpin of the whole stack, where almost everything that we provide as a service runs on Hadoop. And so I'll talk a little bit about the cool things that we have done inside Hadoop to make that happen. And we'll talk a little bit about Hive, because that sort of, from our customer base, that turns out to be the most popular sort of, analysis tool that people use. All right, so Hadoop as a service in the cloud. So let me again start with the product vision of what we wanted to build, and then I'll go into how we built it. So when we started doing this, what we saw was that there are existing Hadoop as a service offerings from Amazon. There's EMR, and there's probably other sort of like open source software that you can sort of like spin up yourself. What we found was that it's too complicated. You have to understand a lot of concepts. You have to understand how to size your clusters, what kind of machines to use, how to configure them correctly, and so on and so forth. So we really wanted to, this is a very overused term, democratize this whole stack. And so a key part of that was making Hadoop really easy to run in the cloud. So here's where we ended up. This is the extent to which you have to administer a Hadoop cluster with Qubole Data Service. So you come in, you create an account, and then you say, okay, well, I want my Hadoop clusters to range in size from 4 nodes to 30 nodes, 1 node to 10 nodes. Choose your favorite numbers. Set a machine type. And I'm going to talk a little bit more about this on-demand stuff. Set like some kind of, okay, what kind of instances you want to buy. So the administrator does this once, and that's it. You're done. After this, the users from the company can just start. So once you've done this, you don't actually get a cluster. You just get a configuration, right? Next, what happens when people log into the system and start running queries? We spin up clusters for them automatically. There's no operator intervention required, nothing. Like everything is automated. The really cool part is that, of course, you don't have just one user, so you have lots of users, right? So what I've shown in this picture is, there was one analyst who came in, and then there's sort of another analyst who sort of came in, and maybe the second analyst ran a much larger query. You also have like some cron jobs. Try to use a robot to sort of show that are running in the background, also queuing up jobs. And maybe the cluster is not big enough at that point to handle all of the workload that has been thrown at it. So what the software does is it says, oh, looks like there's a lot of stuff coming in. Let's make the cluster bigger. And then at some point, your users go away, your workday is finished, and the cluster starts scaling down. And eventually, in the night, you end up probably at the same place where we started, which is you had no machines running in Amazon or whatever cloud to begin with. So, this is like really, really easy to use. This is sort of our what we wanted to build as a product, right? So now going into so another thing I wanted to mention was that one sort of interesting challenge is that these clusters come and go, right? So if you have run jobs in the past, how do you come back and see at what has run in the past? What kind of performance you got from them, and so on and so forth. So part of the vision is that you should be able to come back and look at stuff that happened in the past, right? And those are interesting things to sort of solve, right? So so I'll go into a little bit into like how did we build this? So what are the key elements required, and what are the difficulties in each one of them? So step number one, when you log in and you start running stuff, you have to spin up a cluster. Sounds pretty easy, except not everything needs a cluster, right? So if you come in and run a explain, right? You say, okay, explain, select blah group by XYZ. Right? That doesn't need a cluster, right? You just sort of like, look at the query and come up with the plan, right? So we had to like, go underneath the query engine and find out, exactly what are the places where a cluster needs to be brought up. Second one, if you need a cluster, we need to spin one up, right? But even it turns out even something like this is reasonably interesting because you've got like multiple users coming in. They're all trying to like, maybe latch onto a cluster. There could be race conditions. So, you had to spend some time sort of figuring all this out. And you're also dealing with the cloud provider. So there's sort of interesting sort of like, issues there in terms of concurrency. Third point, once all the users are gone, like you shut down the cluster. Again, it sounds very simple. Very interesting sort of problems that actually some of them we still don't have good answers to, right? So let's say you had, I spun up like 10 nodes over a period of half an hour, 1 hour, whatever. I started them at different points in time. So if I'm going to try and optimize your spend and bring it down at the right time so that you kind of get the most bang for your buck, what would be that time? Would it be the hour boundary of the master because you already paid for, in Amazon everything gets billed by the hour, right? So you shut down on the hour boundary of the master, or you look at all the nodes and stuff. So it's pretty interesting issues in terms of how to best do something even as simple as that. Another simple example is we've added some concepts around like temp tables. These are like very simple concepts that are available in other databases, but not in Hive. But in this case, it makes a lot of sense because as part of your analysis, you want to store data in HDFS. But HDFS will go away once the cluster goes away, right? So we've added sort of this notion of a temp table, and you can create a temp table in Hive. It will be backed by HDFS. You could bring in some data in it, do some crunching, and then once the cluster is gone, the temp table is gone. It's all sort of cleaned out for you. But sort of related to this is that when users are sort of doing stuff, there might be a little bit of idle time, right? I might go get a coffee or something for 5-10 minutes, but I don't want the cluster to be just shut down, just because I just went away to get a coffee. So we have added some notion around user sessions. So once you log in, you get like a hour-long session and stuff. And we make sure that no user sessions are active when the cluster is cycled down. So to provide very predictable sort of as I mentioned, we need to show you old history of all the jobs that I've run and stuff. So we've kind of set up all kinds of archival automatically. Everything is sort of mirrored to S3. When you log back in, it just looks like, yeah, I ran this job like a month back, but the cluster was like torn down a month back. But you can see everything about it because everything is stored in the cloud storage system, and you can sort of continue to visualize it. As I mentioned, like there's so many different node types. You don't have to think about, okay, like this machine has 4 disks, 2 disks. As a result, the Hadoop cluster configuration has to be different based on the number of disks, amount of memory, number of CPU cores. So we've kind of taken care of all of that stuff. For every instance that you launch, we optimally configure the Hadoop running on that instance to have the right number of, use all the drives, use all the memory, use all the CPU. The final point is the most interesting point that we learned as part of building the service is that so many things keep going wrong when you are doing this kind of stuff in the cloud. Like you request, for instance, but then Amazon doesn't give it to you, but after some time it decides to give it back to you, and then like if you are not careful and if you don't come back and check whether you have like runaway instances lying around, then you would just like sort of keep paying money for them. So we've added lots and lots of sort of background processing to keep checking the clusters, making sure the nodes are good, that we only have the nodes we want, not the nodes we didn't want, that all the nodes are actually healthy, the cluster is healthy, and so on and so forth. So most interesting part in building this was the part that I haven't mentioned yet, which is the autoscaling part. How do you scale up and down, and what are the complexities associated with that? So I want to give you a little bit of a visual walkthrough of how the scale up, scale down happens, particularly the scale up. So this is also a sort of a good way of, for the people who don't know Hadoop internals to tell them a little bit about how Hadoop works internally. So what you see in this slide is a standard setup, like you have like 3 slave nodes and 1 Hadoop master node. The master node is just sort of blown up so that we can look inside to see what components there are. What I've tried to show in this picture is that initially the system has no work. There are a couple of queues, the queue of map tasks and reduce tasks. Both those queues are empty, there's nothing to work on. And there is this thing called the job tracker, which is the thing that sort of takes all these little pieces of work and sort of moves them, schedules them at different places in the cluster. There's also another component mentioned, Star Cluster. Star Cluster is a project from MIT which helps orchestrate master-slave cluster architectures in Amazon, and we've sort of used that to build our service. So I'll just sort of put that up in the slide. All right, so let's see what happens now. So the analyst comes in, types in a query. What happens when he runs that query is that Hadoop sort of says, oh, I've got to like chomp on like 10 gigs of data or like 1 terabyte, whatever, right? It says, okay, here are like the 20 pieces of work that I need to do. It has some pieces that have to be done inside mappers, some that have to be done inside reducers. And now it's the job of the master node to go out and run these across the distributed, all the nodes in the cluster. So the job tracker says, cool, great, I have something to work on. It says, I've got 3 slaves, so here slaves, like go take this work, right? Every slave can only run a certain amount of work. It can't run like everything at the same time. So it takes part of the thing, some of the workload that has been queued up, gives it out to the slave nodes, but some of it stays queued behind. And obviously the query can't complete until all the work is done. So this is a good time for us to potentially consider autoscaling, right? So what we do is we get progress report from the slaves. This is not something we added. This has always been there inside the Hadoop stack. It is used for reasons other than autoscaling. It is used for speculative execution, which is a very integral part of Hadoop. But based on these progress reports from the slave nodes, we are able to figure out, well, how many CPUs do I have right now? And are these enough for me to finish the query in some bounded amount of time, right? So a simple look at supply and demand. And in this particular case, if we find that the demand is much more than the supply of CPUs, we go ahead and tell Star Cluster and Amazon, hey, give us some more nodes because this is not enough to get the job done. At some point, a little bit unpredictable, Amazon gets back and gives us some more nodes. And at that point, the job tracker can now say, well, cool, let me take the rest of the stuff that's queued up. let's dispatch that, and like we're all cool, right? And so of course, so very simple stuff, but very, very effective, because now you can just throw anything at this, right? It's not one user, one query. You can just like put all of your users, all of your queries. You just have to set the min and the max size for your cluster, and you're kind of done, right? So this was actually the easy part. Scaling down is really hard. The reason it's hard is that when you add things, it's not destructive. You just add like CPU capacity, disk capacity. But when you remove things, what happens is if you just take away the disks from Hadoop distributed file system, it doesn't like it so much. And especially if you take away lots and lots of nodes, then it doesn't like it at all. And at some point, it will say, oh, like half of my blocks are missing, I'm corrupt, right? And stuff like that. You don't want to get there. So we did a lot of stuff around scaling down, which is, first of all, we find out, okay, this node is coming up on the hour boundary, so if there's no work in the system, maybe this is a good time to tear it down. But once we make that decision, we very carefully orchestrate a series of steps where we say, okay, well, let's stop like running stuff on it, and then let's tell HDFS that we want to take this node away, so that, no surprises, HDFS gets its chance to sort of move data around. If there's any vital data on that node, it gets to put it on some other node, and so on and so forth. Specifically, one thing that we did, maybe we'll talk about it when we get to the Hive part, is we use, since HDFS just sort of comes and goes, it's not long-lived like in a usual Hadoop cluster, we use it quite often as a cache. Because the performance of S3 and cloud storage is not super predictable, so we use HDFS as a cache. So there are interesting things you can do. You can say, well, if most of my data in HDFS is a cache, when I am deleting a node, instead of bothering to re-replicate the data, keeping it alive, I can just go ahead and like wipe out the parts of the cache that would be affected if a particular node was taken away. And so all of that stuff is sort of happens in the background when nodes get deleted. All right, so wait. So that's sort of the basic part. Now, one of the other things we did was Amazon has this really cool thing called spot instances, which I'm not sure how many people know about. But what spot instances allows you to do is essentially bid for machines instead of buying them at a fixed price. And normally, you get a much cheaper rate. We have seen rates as low as like 10% of the regular rate of a machine. If I were buying spot, I would get it at 10% of the price. It varies a bit. We've seen it on an average at least 50 to 60% cheaper. I'm sure they're not as cheap at Christmas time, but So we've added support for spot instances in Qubole, and this is sort of a little bit more advanced. So now I said, okay, well, let me use spot instances with my Hadoop cluster. And the only thing you again need to do is say, okay, well, how much am I willing to bid for it, right? And the easiest thing to do is to say, well, let me just bid like 100%. I mean, I'll bid like if the regular instance costs $1 an hour, I'll just bid $1 an hour. And it's a second price auction, so Amazon will give me most likely a much lower price, even though I had actually bid $1 an hour. So there's a lot of sort of detail here about spot instances and stuff I won't go into, but from an operator point of view, your configuration is fairly straightforward. We have decent defaults in place. But the one challenge is, so the first part is bidding, so and we take care of that, fine. So now we'll bid on your behalf, get the nodes. If the bids don't come back in time, we will sort of time them out and get regular instances. So that's all like really easy stuff. The hard stuff is that once you get spot instances, there's no guarantee that you will be able to hold on to them forever, because they are bidded instances. So Amazon reserves the right to sort of take them away from you as soon as, let's say, your bid is not high enough. So that presents some challenges because going back to HDFS not liking nodes being taken away from it. Well, what if Amazon just comes in and sneaks out, takes out the carpet from under us? HDFS will simply like die. So we have done some interesting stuff where you can choose a hybrid mode for your clusters, where we keep for any data that's stored in HDFS, we keep one copy on a regular node and one copy on a spot instance node. And that way, even if Amazon sort of, it never happens, but just in case, on Christmas Day, they just decide to pull all the instances down from under us, we're still good. We've got like one safe copy of the data, and we can sort of tolerate that loss. Right. Okay, so let me shift gears a little bit and talk about Hive. We've also spent a lot of time tuning Hive to work much better in the cloud. So again, going back to like what is the product vision? The product vision is that Hive is a way of analyzing data. So you should just write queries and not have to think about setting up systems and all this stuff. So what you see here is a snapshot from a slightly old revision of our software, which keeps changing all the time. We push very frequently. We have an even better UI now. But what you see is like a query console. You can look at all the queries that you have run. You have a little composer where you can type in new queries. You can download results from your own old queries. You can look at the logs and all this stuff, right? Pretty basic stuff, but it's very convenient because you're dealing with a system that's coming and going. But as part of the service, what you are getting is a place where the things that really matter to you are captured persistently in our systems and in storage systems like S3. So you can come back and get your results anytime you want for things that have run previously, for example. The other thing that we saw was that there's a lot of talk about performance in this conference, but there's only a certain extent to which you can fix performance, right? I mean, if you're talking about analyzing like terabytes and terabytes of data, it's going to take a little while. And one of the things that we have found persistently in our interaction with analysts is that oftentimes they are authoring queries and they want to figure out whether the query is roughly correct or not, right? And once they've kind of figured out what the right query is, then they are like, yeah, fine, now let's go and run it on a terabyte. But while I'm not still there, let's just run it on a small set of data. Inside your company, the cost angle of this is not much. I mean, yeah, there is the latency angle, but from a cost point of view, you already paid for your cluster, right, if you are running a large Hadoop cluster in-house. But in the cloud, thinking separately about test and production is could have a dramatic impact on your cost. Because when you want to just run a query for test, you don't need that big 30-node cluster. You just need like the small 4-node cluster. So many of these technologies are there in the Hadoop Hive stack. I mean, we've added some, but the problem we've seen is that they are not exposed very easily. There are like arcane options. You have to remember, set some option and all this stuff. And like, it just doesn't work for an everyday usage scenario where the analyst is just trying to get their job done. So we've kind of sort of done some back-end and front-end work to sort of make that better. Let me just focus on the sampling part. So there's like little check boxes. So if you type in a query and say, okay, let me run this in test mode, right? And the system automatically sort of goes off and says, I'll find some like 100 megabytes of data that sort of looks sort of like a good sample for this to run on, and it won't cost you much, right? Because you don't need a big cluster to do that. Right, then there was the other part about we also store a little sample of the data in MySQL. So that way, like one common problem is you're trying to do some regex on some column, but you really need a cluster for that. Probably not, right? If you have a little sample of the data stored away, you could just try that regex against that sample. So we've also sort of built some support for things like that, right? Right. The second part that I would focus on is that we've done a lot of performance stuff in Hive. So let's see. All right. So if you guys are like, if any of the people are Hadoop veterans here, you would know that Hadoop has a really tough time with small files. We spent a lot of time in Facebook sort of building a bunch of stuff, combined file input format and stuff that made Hadoop work reasonably well. Those problems like become a lot worse in the cloud because you're dealing with the cloud storage system that has much higher latencies compared to HDFS. So we've done a bunch of stuff that helps essentially small file computation possible against data stored in S3. Anecdotally, we have heard that if you just take stock Hadoop Hive, the open source ones, and just sort of like try and install it, it just sort of like doesn't work. I mean, there's just so many versions and stuff floating around. It's just very hard to get the right version with the right set of patches that just sort of like works well. The techniques are fairly straightforward. When you are like reading small files, well, as you are reading one, maybe you can start reading the next one, right? Prefetching, pretty standard techniques in sort of people who build sort of programs and stuff. Things that are advertised to work with Hive but don't, unfortunately, and we will be giving some of these things back to the community. So there's this thing called JVM reuse, where you can say if I'm running the same query on the box, and like there are lots and lots of tasks belonging to this query, I don't need to spin up a Java virtual machine every time because that has a lot of cost. So I can reuse the same JVM for at least for this fun query. And we're actually working to extend this across queries. We are actually even discussing some of this with Hortonworks as well. But there are a lot of sort of small bugs and stuff in Hive and Hadoop, which kind of well, this is not too stable. We fixed it. It gives a fairly dramatic speed up at least 1.2 to 2x. There's stuff that Amazon sort of did half a job. S3 is a weird file system. It has no move operation, and this is one of the things that sort of like is so difficult to deal with, because the whole Hadoop stack is architected with the assumption that file systems have essentially a free move operation, right? Just like in any other file system. But in S3, there is no move operation. And even worse, the S3 file system in Hadoop says that there is a move operation, but actually it's a copy operation. So what happens is when you do a move of a terabyte file, that poor client that issued the move is actually like fetching chuck, read 1 terabyte, write 1 terabyte, and it's like, obviously you don't want to do that. So there are some obvious things we had to do to sort of get around this. Basically, you have to be much more careful in writing data out to your final location and not depend on the move primitive. And the move primitive is very useful to do atomic stuff, right? Because you can sort of like write some temporary data and say, oh, looks like everything is done, so I'm going to move it to like some final location. When you are doing things in S3, you cannot do that. You have to write it to the final location and then take a second pass and say, well, if I didn't get it right, I'm going to go and delete stuff and things like that. So those are like without these optimizations, Hive and Hadoop on the cloud are like practically like not very interesting. I mentioned that we use HDFS as a cache. We found this technique particularly effective with data formats like JSON, which are very expensive to parse. So what we do is we read JSON data, and we know the columns that the user is interested in because they've already defined a table over this JSON data. And we take these columns and store it in a columnar data store on HDFS, which is purely a cache. And then all the discussion I had about if it's a cache, nodes go away, you can sort of deal with it differently, all that kicks in, right? But the end result for the user is that running repeated queries on JSON data in our system is dramatically faster because of the caching that we have put in. Finally, very small and interesting things. When we started off building the system, every time somebody would run a query, we would sort of spin up a JVM, compile it, run it, and so on and so on. And it's ridiculous. People said, what, it takes me like 20 seconds to just like do an explain on a select statement. That's not acceptable. So we spent a lot of time building a multi-tenant Hive server, because Hive server is just a persistent sort of a container that can help you sort of compile and run queries. Except in a service setting like us, it's very complicated because we don't want to bring up a Hive server for every account that we every customer that we provide a service to. That just wouldn't scale. So we have a very nice multi-tenant Hive server where it's all secure and stuff, but all the compiles is done against one JVM, and that way everything is, from the customer perspective, everything is a lot faster. And that brings my talk to an end. So there's a free trial available. Anybody can sign up if you are sort of in the cloud. If you have data in the cloud, you just sign up. Go ahead and just type some queries and see if it works for you. And we are here for feedback and to help you. So that's it. Questions? Yeah. No. No. I'm not saying that at all. It's just that when we have started off in Amazon, for obvious reasons, because it's the most popular cloud, we are definitely looking at other cloud vendors and trying to figure out. We are starting to do some prototyping in Rackspace. We've also talked with Microsoft. Those are ongoing discussions on what we can do in Azure. Yeah. It's not yet there. Yeah, we're definitely looking. Yeah. We are supporting multiple regions in Amazon. So Amazon itself has like US, Europe, and stuff. So this is almost like release. So we do like if your data is in Europe, we will spin up your machines in Europe. So that's sort of our first sort of step at sort of generalizing our service. And we are hoping that we'll take the similar step for like something like Rackspace, where we'll say, okay, your data is in Rackspace. Now I will spin up your machines and clusters and everything in Rackspace. So in general, our model is that we treat the cloud like hardware. So we are like a software vendor. So you have your relationship with Amazon or Rackspace or whatever, and we just sort of like help orchestrate stuff for you. You don't pay us for the machines. You just go and pay Amazon or Rackspace directly. can you repeat that? How reliable?
Okay, how reliable do you have any
Yeah, so one of the things we have done is sort of used a standard recommendation. This is something the Netflix guys wrote about, is that we recommend our customers use in any given machine class, the largest possible instance in that machine class. What this means is that you are the only application running on that bare metal machine. You're not sharing, you are not a virtual machine contending with other virtual machines for the same machine. I haven't done a lot of tests, but so from that perspective, we try to isolate ourselves from sort of performance variance. But there are other reasons for performance variations. So like EBS is a very well-known reason. We try not to use EBS drives at all. So we try to use EBS drives only for booting our machines up, but all the data storage, HDFS, everything happens on sort of locally attached disks. The final part is networking performance, and especially S3 performance. We see a lot of variation. That is why we have invested in caching. So I talked about the columnar aspect of the cache, but actually just the fact that you store it in HDFS means that you can get rid of the jitter to S3. So we're definitely interested in that. So we don't do that. Typically you configure the cluster to be of one machine type. So far we haven't seen a need to support different machine types in the same cluster. I mean, it's just like unnecessary complexity, like why go there? None of our customers seem to have wanted to have complexity like that. We do use a different machine class for the master node because it just doesn't need as many compute resources. So we tend to use a smaller machine for that. Within the same class, as I mentioned, we try to use the biggest virtual machine possible. Yeah. No, we do. I mean, it's extra large. So if you use, we leave some decisions up to the customers. Our default setting is M1.extra large. M1.extra large takes, takes whatever M1 machine bare metal is, it takes all of it. And then Hadoop is pretty good at evenly striping out load across different nodes. So we do take care of that. There are actually interesting problems that I have not been able to go into. Scale down is actually fairly hard. One of the things I didn't mention, which is, if you have time left, is Hadoop has this model where, if you have just like one reducer like hanging around, Hadoop says, I still need the map outputs on all the nodes. So you see your mappers ran on like this 10 node cluster. We've got like one lone reducer, slowly sort of like, like trying to finish up, right? You would think that you would say, oh, let me get rid of the 9 nodes. Let me just go down to the one node on which this reducer is running, right? Because it might actually run for a long time. Turns out it's not very easy with Hadoop because the Hadoop framework thinks that all those 9 machines, other machines with map outputs are actually still interesting because I can't explain. It's too complicated. And so there are like very interesting technical problems that we are still have to solve along these lines, and we'll sort of get around to it. Great, thank you so much.